Welcome everybody to today's Tech Talk. We're really happy today to welcome Graham Hawkes, he's been working on this winged submersible for the last 15 years and about 35 years of other kinds of manned and remotely controlled submersibles before that. Founded a bunch of companies in this business and basically produced all of the deep diving submersibles that people have used to explore the world's oceans. And I think this is an incredibly interesting and exciting opportunity for Google to get involved in these kinds of things, maybe take some pictures or something. Graham, tell us how it works.
Well, thank you. I just met a guy who's got, how long is that thing?
19 meters.
19-meter concrete submarine. That's the first. Is there anyone else here involved with Google Ocean or ocean-connected stuff, or is this just all general? Just ocean-connected stuff? Okay. Well, look, we've all been to too many talks where the subject is going to save the planet, and it's all incredibly important. I'm going to try not to go there, okay? I think the common theme in engineering and exploration is that people do it for passion and get a big kick out of it. So part of what we're doing is we're going to show you is the birth of underwater flight. But before we go there, you're just going to have to bear with me a little bit because perhaps it is important. So just a couple of statistics. And I don't want to tread on anybody's toes, but Earth is a really stupid name for this planet. It turns out 94% of life on this planet is aquatic. We all know 2/3 of the planet is ocean, but that's misleading because it's a three-dimensional place where the average depth is 4 miles. I don't know how deep is your sub rated? 300 meters. So you're near surface. So average depth of 4 miles. And you compare that to the terrestrial habitat, which is really a thin film. So it turns out that as a habitat, if you want to weigh one to the other, this planet, we rather stupidly called Earth, is about 94% an ocean planet. We're in a 6% minority. And that is a problem for a lot of people who would prefer that I don't know. It just doesn't speak to the idea that this planet is human-centric. It's a maturity, it's an understanding of who we are and what we are that we've yet to rise to. Okay? And let's just leave it at that. So what we're trying to do is get access to not 2/3 of the planet, but was it 19/20? We're trying to get access to this planet. Turns out we don't have access. And we've looked skyward, but we just haven't looked downward. So I don't know if there's anybody here, but occasionally if you give a talk, you can find there's a billionaire or two in the audience building rockets. There's actually 5 in the US. Those rockets are 180 degrees off course. This was 1930. This is kind of where it started. This was William Beebe, and that hollowed out cannonball there, lowered by a cable in the 1930s, created quite an excitement. Barton and Beebe crawled inside, got locked in. They went down 3,000 feet and saw very strange things. And that was the first kind of human contact into that deep space. That was 1930. You would think that by now we can all go anywhere, anytime we want. That's not quite the case. After Beebe, the next kind of big thing in terms of vehicles and manned vehicles were, well, the latest and greatest is Shinkai, which is Japan's entry into deep submergence. It's rated to, I'm not sure, it's rated for 6,500 meters. It's about 23,000 feet, built in 1989, and really the last of the big ones. This is the most recent sub, single one owned by Japan. China is now building one, and there are only 5 deep subs on the planet, okay? 5. They probably move at a 1 to 2 knots, irrespective of other claims. That's probably where they are, 1 to 2 knots, maybe 2.5 knots. Require a mothership to operate. In the bottom right-hand corner, there's Atlantis. That's the mothership for the US single deep submergence craft, which is Alvin. Only 5 in the world. Lots of problems with them. This is probably the least of them, but I think this is funny. There are chairs inside these submarines, submersibles, and people peer out of portholes and go down deep. Sorry, but I think that's a pretty fundamental problem. The next kind of milestone, perhaps, if you'll allow me to say this, was that some of us built shallower, but really much more friendly subs. This is one of mine. This is Deep Rover 2. There were 2 of these built, and sitting in that is James Cameron. And Cameron used 2 of these in a really interesting film, Aliens of the Deep, showing deep subs, the Russian mirrors down at vents. Areas in the ocean where 2 plates come together and create kind of volcanic type activity. Thermal vents where seawater is taken down into the Earth's crust, superheated, and comes blasting back up. It's a chemical and biological laboratory. Others found vents in 3,000 feet, the depth rating of these subs, and so Aliens of the Deep use these 2. So I'm going to suggest that this sub you're looking at there is the pinnacle of conventional submersible technology. We need to throw it all away and start again. Now, you won't hear many people say that because some are still trying to raise money to go back and build big clunking submarines. Remember, there's 5 on the planet. China's building 6. And some people want the US to have numbers 7 and 8. If anyone's into scale, it's you guys. So I'm suggesting 7 and 8 doesn't make any difference. You need 7 and 8,000 perhaps. This is a big planet. We need something brand new. We need to start again. Here's the fundamental problem. And this is where our lab, which is up the road, parts company with almost everybody else. The strange thing is no one's following us, so perhaps we're wrong, but you be the judge of this. Here's what we think is fundamentally wrong. There's 5 subs clustered there. One of those, the one on the far right the one on the top is Alvin with the US flag. Alvin is an heroic, much loved piece of US technology. It gives access to the deep ocean. I'm the only one standing up and saying it's a complete failure. But I have to really qualify that. Not for Alvin, not for the crew, not for what she's done. She's done great work. But she was designed and built in 1950. She's 50 years old, a prototype. So how many of you are working on projects where you're building prototypes, and in 50 years, if that's the only one that still exists, was that successful? No. Didn't work. Didn't change much. Didn't get to any scale whatsoever. That's the problem. And here's the problem with it. That bottom axis there is weight, thousands of pounds. So look where those 5 are clustered, and the one that China's building is probably going to go off the scale to the right. So here's the problem that we see. It's the weight. So if I can build you one of these subs that weighs 60,000 pounds and deliver it to you because you want a submarine for $1, right? Your problem is you're going to need one of those things in the top to launch it. That's a mothership. 20 tons of fuel oil a day. It's going to drain your pocket 24/7, tied up somewhere with a crew of 50. Are we wrong? No one else gets this. No one else is where we are. It's the weight of these things. That's why there's only 5. Only 5 subs. So I put that weight barrier at 10,000 pounds. Why? Because if we can get under 10,000 pounds, we don't have to own our own mothership in the fleet of oil-filled support vessels, in the fleet of national research vessels. Typically, they will have an A-frame on the back or an articulated boom crane, and typically that can just about manage to launch and recover about 10,000 pounds, roughly. So what our little lab's done is said that manned subs are dead. There's no scale effect unless we get under 10,000 pounds and get rid of the stinking mothership that we don't have to own. That's it. So I'm going to leave plenty of time for questions. You tell me where we're wrong. In order to get that weight down, we had to do one thing. Submarines, conventional submarines, displace their weight. They're typically neutrally buoyant in the water. Ours aren't, but all the conventional ones are. So weight is a function of volume, by definition. Volume is, if I take 3 of you, sit you on chairs, and draw the smallest volume around you without you having to contort into some extreme position, stay like that. I've just defined a sphere of probably 60 or 70 inches internal diameter. Figure that out with titanium, the strongest material we've got, right, wrong, but never mind, that's where everyone thinks. A sphere is the best solution, right? It actually is, but we can't afford it. So figure out a sphere around 3 people, bingo, 60,000 pounds. You want to get to the bottom of the ocean, 100,000 pounds, mothership, dead, finished, gone, dinosaur, forget it. You're going nowhere. You're going to dive in the ocean the way that Japan is, costing $80,000 a dive. You're going to dive once or twice or 3 times a week. That's it. No scale. You don't match anything. It's so last century stuff. To get the weight down, if it's possible, you just have to get the volume down. So you have to take this round pressure hull and shrink it around you or you. You just have to do that. It's no longer round. Titanium is no longer good enough. That's just tough. You just have to try and figure it out. So now perhaps you understand some of the issues that our little lab decided we could solve and nobody else ever thought we could, I think. Nobody's followed us. Nobody else is saying we've got to get rid of the motherships. Nobody else is trying to build subs under 10,000 pounds. So we're either nuts or we're right.
Both.
Both. Well, that's interesting. I don't deny either of those. Okay. So this was a design concept that we actually were nuts enough to build. And Karen and I launched that in 1996, Deep Flight 1. The whole idea was to shrink a pressure hull around a human being and imagine the pressure hull, because we couldn't afford to do it, that could take full ocean depth. So titanium doesn't work, but ceramics do. Ceramics do. Ceramics have an interesting property in compression, and only in compression. They kind of behave like a liquid, like a fluid. At the bottom of the ocean, the Marianas Trench, 16,000 pounds per square inch, water exists, and if you flopped your hand through it, it would feel like water on the surface. There's only a second order increase in density. It's just impervious to pressure. You can't push the molecules that much closer together. So there are now some mechanical engineering materials that behave like a fluid, and glass is one of those, by the way, that potentially give us the ability to build pressure hulls that take enormous compressive stress. So if you look up the compressive stress of glass, you'll probably find somebody's reporting here that 200,000 pounds per square inch. Titanium is going to fail at about 130,000. The 200,000 figure for glass is all over the place. It's probably because there's a flaw. The reality is, if that was pure enough, you probably can't squeeze it enough. In reality, it will break at some point. However, take that piece of glass and pull it, and it just pulls apart. So it has zero tensile stress. So I'm talking about a glass that you drop and it smashes, and I'm saying you can build a submarine out of that, and you're saying you're nuts. But I'm saying, well, it's because if we can engineer it just purely for compressive stress, we're okay. But bring it to the surface and bump it into a dock, and you've got big problems. It just cracked around you. But there are some engineering ceramics. So that's what we were looking at with this. The pressure hull there is mainly cylindrical, half as efficient as a sphere, but there are some potential materials that can handle that. The pressure hull is shrunk around the human. Its volume is low. That sub displaced 2,700 pounds. Potentially, the geometry we used in there could go to full ocean depth with the right material. But there's another issue. If the pressure hull is that small, how long is it going to be comfortable for? The existing deep subs are underwater balloons. They're going to take 6, 8, if you went to the bottom, 12 hours to sink down. You're taking a thermos flask, you're sitting in a chair, you've got some means of dealing with bodily issues, which we won't need to get into. And you're cold, uncomfortable, but you're in there for a very long time. We call that hotel accommodation. In the hull form we're looking at is much more like a pressure chute. There really isn't hotel accommodation. You're going to be comfortable in there for 3, 4, 5 hours. Don't ask me how, but we know that. You also all know that. That's what you'll drive down the freeway before you start looking for a rest stop. Then you get out. Small aeroplanes, spacewalks, the future of deep submergence. That's the time scale you're looking at. So take that time scale and look at full ocean depth, which is vertically 7 miles away. That means we had to set the idea that we could only spend 1 hour going down and 1 hour coming back. Numbers are pretty simple. That means we're vertically transiting at 7 miles per hour. Doesn't sound like a lot, but water is 850 times as dense as air, and these underwater balloons are never, ever going to achieve that. You're never going to get down and back that quickly by ballooning underwater. So it turns out you actually face the same problem that existed over a century ago by trying to master airspace and transitioning from ballooning to fixed-wing aircraft. I haven't got time to really get into that. You can challenge that in questioning, probably will, but just trust me, the math is the same. To a first-order approximation anyway, to a few percent approximation, the math is the same. It turns out if we're going to get to the bottom of the ocean, if we're going to move through the water at 7 miles per hour, the drag goes up with a square. That's from 2 miles per hour, which is currently realistic in underwater ballooning, to 7. Call it a factor of 3. The drag goes up with the square, the power goes up with the cube. It's just not going to work. You just can't get a balloon from Europe to here carrying people, and it's just not going to work. It's just not going to work with humans in this vast dimensional space ballooning. So you got small pressure hulls, limited time. We've got to learn to fly underwater. It's just that simple. It really is. Hence, this thing had wings, had no buoyancy system, didn't look like any other sub. The control systems inside had to all be kind of cleared out the way. I'm actually claustrophobic. That's me in there. I was going to be the only pilot of this crazy machine. So maybe you're right. You see this bar that goes through here. Anyone in this room is claustrophobic may start appreciating this. It's really interesting. It turns out, because I know I've been in these small machines, the whole idea of being claustrophobic is visual. So we can take anyone who says they're claustrophobic. Anybody here will admit to it? You all are to a degree, I promise you. Okay, Shannon, if we put you in a spacesuit or a hard suit that's totally confining to you, but your head is clear, you're happy. Stick that helmet on and you start screaming. Take the helmet off and you're happy. It's visual. Up. Unhappy, happy, unhappy, happy. I know that. And so this thing is right there, is structural, but it's back behind my peripheral vision. I can't see it. And I'm smart enough not to stick anything in front of me there that tells me I'm in anything. And the refractive index and geometry of this front dome here is very close to that of water, which means you have a wonderful thing. If you take a window in a vehicle in aircraft, you're aware you're sitting behind a window. We can adapt the geometry in underwater craft so that that window, when it closes down on you, you can see right here, that's claustrophobic in there. Underwater, that's optically dissolved. Underwater, the psychological effect is your head is out there and you're a whale. I mean a fish. I don't mean to, you know what I'm saying. So I'm in there and I think, gosh, I keep telling people, but it blows my mind every time. I don't know where this dome is. And I put my finger out and I don't know when I'm going to touch it. At some point, it just folds up. It's the coolest thing. It's not claustrophobic. But this was an underwater flying machine, and it was meant to get us through to the next generation of working man subs. And this was published in New Scientist years and years ago. It shows how we hover with vertical thrusters. It shows that we're stopped. We've got manipulators. It shows how each one of these modules, there's one person in each one. They are completely self-contained, so they can be attached. This is a one-person submarine. That's a one-person submarine. They're united together. We came up with this incredible idea of a land system. I'm being funny about that. So there's two-wire connection in there, computer, software. So in one is a passenger, the other is a pilot. And sandwiched between is a complete work package, however you want. 4 manipulators, which is ridiculous, but we're making a point. Full hovering thrusters. Published years and years ago. That's how we stop and hover. That's how we work. We can now make that. We've now published that. That will cost you about $3 million for one of these. Full ocean depth sub. The whole set weighs about 10,000 pounds. You don't need a stinking mothership. We're there. We're done. I'll show you a sub that we built for 37,000 feet. And guess what? The US just spent $27 million on a design study to upgrade Alvin. They could have bought 3 new ones and no stinking mothership. People don't believe where we are. They just don't believe it. I'm just letting you know. Letting it all hang out there. So I'm going to go through and tell you what happened next and where we are. When we launched that Deep Flight 1, it was publicly launched in Monterey. I promise you, you're welcome to come and look at it. It's in our workshop up in Point Richmond. It's tiny. It looks incredibly uncomfortable. It actually isn't, it just looks it. And before we launched it, before people saw that in the water, almost everybody would walk by and they'd shake their head and go, "You'd never get me in that. You're nuts." However, after we launched it, I was flying around as happy as a clam in Monterey. Wanted to see what was happening with the press. I mean, a press launch of a submarine is a funny thing because you go down and it's gone. So trying to look and see Karen on the shore, I would just jump this thing up and look around, and it would disappear down, and the crowd went, "Whoa," started clapping. I was running with a support boat. I was nervous that they were going to run over me and destroy me, so I would porpoise out of the water like, "I'm here, don't run over me. I'm here, don't run over me." But I'd learned to porpoise like a dolphin. It's to do with the wavefront. The thing has pretty low drag when it's submerged, but as soon as you break the water and generate a wave train, the drag increases. So within 2 or 3 cycles of that, I'd simply learned to stick my nose up, look around, and get the nose under that wave and back down. And I could shed that wave with no loss of speed. Afterwards, when I looked at the video, I'm a dolphin. I know why dolphins do this stuff. They're looking, but they're not getting the penalty of a wave train. They just wave, whoop, underneath it. It's the coolest thing. So that in itself changed a lot of people's perception. And when we came back out, I noticed a lot of people sidling up to this thing and kind of patting it with a little bit of a funny grin on their face, and they would imagine what it might be like. And some would say, "It must have been really cool." So, you know what it was designed for? It was designed to get the weight under, but it actually opened up this whole idea of flight and the whole idea of an adventure and fun. So the next thing we actually were funded through a friend of mine to build, we're always limited by funds, but we're a tiny little entity, was a two-place flight trainer. The idea was, let's take flight and see what we can do with it. Forget depth. Let's not compromise this machine by trying to go deep. Let's simply push underwater flight for its sake and see where it goes. So we built this flight trainer. There's Karen, who's right here, is my wife. We had a ball with this thing. Launched it in Monterey off of the utility dock in 20 feet of water, a sandy bottom. It's the most boring place to launch a sub in a planet, but we've always done that because we need to test the thing in salt water, and that's where we go first. So in this dive, there's a reporter in the back who bugged me, but I said it's going to be boring. There's not much point, but I'd take you anyway. But now for the first time, we're flying, and boy, is that different. We're moving underwater. We go through a cloud of jellyfish, looking at the underside of waves that are kind of streaming over you, flying through this beautiful cloud of jellyfish. And then the reporter behind lets out a blood-curdling scream. He's obviously dead or very close to death. I mean, it was the most amazing scream. My head snapped around to see what it was, and all it was this guy, a big sea lion who, incidentally, with conventional subs, just get the heck out of the way. They're bored and they move away. But we had this sea lion stuck on that wingtip about 6 inches off, head forward, focused. He's like, "I don't know what this big blue thing is, but I'm its wingman. That looks cool." We just had an escort. And by the time I turned and looked at him, the sun went black, a big shadow went overhead, and it was another even bigger one that did a barrel roll, dig a loop right around my cockpit. And this guy said, "I'm better than you. I'm master of this space." And he zoomed off. That was a boring dive. Everything else since then has just gotten really exotic because we're beginning to have encounters with these big animals that we've never had before. So the next thing we did was, wow, we've got to get our signature as low as we can. We've got to get our acoustic, our light, our electrical, any leakage down. We started going to lower voltage, making sure we built in plastics, getting our signatures down. so that we could have these encounters with these big animals. Well, that was some years ago. And then, when was this, Karen? When did Steve come to us?
That was 2005.
Yeah. We've been having discussions with Steve Fawcett for a number of years prior to that. He was interested in full ocean depth. We had some interesting discussions. I wanted to build 2 one-person subs, and we will both go down safe. We can film each other. Steve wasn't interested in that. He was interested in solo record, which meant that he didn't have somebody else going along with him. So all those years ago, I thought about it and said, okay, I don't need that record. It doesn't mean much to me. Steve, we'll build you the machine, but Steve, you'll let me go afterwards, right? I'll get to use it and get to the bottom of the trench. And bless his heart, but Steve Fawcett is Steve Fawcett. He said, nope, no. No, I dive, it goes into Smithsonian, you get the technology. Deal? No. But a number of years later, we called him up and said, Steve, okay, we'll do it. So now we had to put our money where our mouth is and build a pressure hull that actually could take 37,000 feet. Believe it or not, couldn't get ceramic built in that size. If we had been Google or had plenty of money, we could have done, but we didn't. We were on a shoestring budget. But this is the pressure hull we ended up with, and it ended up as a filament wound carbon. It can be done. Just. Can be done. Some of our engineers are sitting in the audience, and we're all traumatized because we ran through a series of tests, model tests, DoD facility, pushing carbon to 37,000 feet, which is 16,000 external pressure. So take a scuba bottle, this thing you're afraid is going to blow up in your face, put it down 7,000 feet in the ocean, and the external pressure is equaled. Open the valve and nothing's coming out. Take it a bit deeper, open the valve and water goes in. And now you're only about 1/6 of the way where we're going with that thing with a human inside. It's a pretty serious problem. And so we set up a number of model tests designed to fail because we wouldn't find the limit of material until it failed. So we built models that were designed to fail within the pressure that we could subject them to. And that's why we're all traumatized, because the rascals never went where they're supposed to, and they made a hellish bang. It must have registered on the seismic meters around the world. I bet those labs knew when we were doing testing. Seriously. This was a pressure vessel buried in the ground in case it ever let go. It would take out the town it was in, but nobody knows. It was serious stuff. But in the end, we think we got there. In the end, we ran a full-size test that if we extrapolated, it was going to be safe. And Steve, bless his heart, overruled all of us and said, we're done. Enough testing, enough money, I'm going to go with it. So the rest of the machine, thrusters, flight control, and here you see our philosophy. The pressure hull is just the minimum we need. Everything else, we imagined we were fish engineers. You know, fish engineers would not build things to work in air that need to be encapsulated, protected from pressure. They would just build stuff that would work in their environment. Seawater is a corrosive, conductive, nasty fluid. Pressure is horrendous, but fish cope with it. They would design stuff that would just cope, and so we did. Everything externally is remarkably comfortable at pressure, and so we ended up building a number of components that were just insensitive to pressure. It just had no effect, no measurable effect. Interesting thing. So the whole machine was built, and that's with all of these components, which will go to 37,000 feet or 37 feet. They don't care. They really are not attuned to the difference. But trust me, that pressure hull is. But we got there. And we were 4 weeks away from launching this machine. There's an underside view of it. It's a front view. It's pretty heavily engineered to work at 37,000 feet, but if you see it, it's in our workshops up in Point Richmond. It's an airplane. It looks like nothing else but an airplane. There she is in the side view. And there's our team. And that's how many people we have. And remember I talked about getting rid of the mothership? Well, that 37,000-foot sub, our prototype, weighed more than we wanted. We wanted it at 5,000 pounds. It weighed 8,000 pounds. But give us a break. It's the first one. It's twice as deep, 10 times the range of anything else ever built, about 1/10 the weight. We'd learned that Steve's catamaran, PlayStation, was it called PlayStation then, Karen, or Cheyenne? If you follow sailing, Steve has set a number of records in Cheyenne, later called PlayStation, or the other way around. It's 130-foot carbon fiber catamaran, gorgeous machine with, it had been dismasted off of Chile. And I called Steve up and said, Steve, you know, we are going to have to rent a mothership to do the testing and your dive. You just dismasted Cheyenne. We can use her and we'll save you a ton of money. By then we knew how to get. Anyway, I was surprised. He said, okay, we'll do it. So there's our mothership, which is in Alameda right now, finished. This tripod gantry would lift the sub up through the middle. There were two 250 Yanmar diesels put in the back there, and she would do about 19 knots with these 250 Yanmars sipping fuel at cruise. That is our mothership. She does not burn 20 tons of fuel oil a day. She runs with a crew of 3, and I can tell you, I was looking forward to having a gorgeous sub on that deck sailing under the Golden Gate Bridge for Guam. We would have created so much mischief had we done that. Here was a sub, 1/10 the weight of anything else. The whole project costing a fraction of what another team in the US had spent just trying to do a study. But, as you know, Steve managed to, Steve was last a month before we launched this thing. So what happened next? What happened next? Actually, we went up and tried looking for Steve. Quite an adventure. I haven't got time to go into that. What happened next was kind of figured out we had some space and time to build our own sub. I built about 65 for everybody else. Time to build one for me that had no constraints. Didn't have a single requirement or a single customer. And my own requirement, bear in mind, we probably could have scraped the money to go to 37,000 feet and gotten on the front page of all the newspapers, but so what? So what? We would have ended up with a very expensive, difficult to use craft. I had a different goal in mind, which was that these guys, their territory perhaps is 3,000 feet, but typically it's 1,000 feet of under. I wanted to be able to move with big animals. We had discovered underwater flight. These things were potentially incredibly maneuverable. These guys cruise at 4 or 5 knots. And I wanted to perfect underwater flight just for the hell of it. That needed a different pressure hull. This was the design we came up with. Remember, we'd just come out of a program with a 37,000-foot pressure hull. So to build one at 1,000 foot didn't seem that difficult anymore. What that meant was we had enough guts, if it's guts, or stupidity, you decide, to be able to say, you know what? Every single pressure hull that's been built has been spherical or round. It's kind of carved in stone. Thou shalt not build a pressure hull other than round. We knew how to use composite material to get enough strength that we could say, we don't have to obey that rule anymore. A triangular section is going to be more comfortable to the human form when we got lower frontal area, and I don't care about depth. I'm going to make this the way it should be, and whatever depth we get, we get. That's the philosophy. There's a different view of that hull. And there is a machine again. The pressure hull, this is a two-person one, connected. Minimum space, all the machinery. And most of this stuff came straight off a Challenger. Most of the stuff will be quite happy at 37,000 feet. Bigger wings, fly-by-wire. This baby was going to fly and maneuver the way that we were going to see what it could do. That's a concept of it, but didn't quite get to build it for ourselves that way. Our second customer, I don't know how you measure your customers. By the way, we measure ours right now one at a time, 1, 2, and 3. But look who we got. First one was Fawcett. This gentleman, you may know, is Tom Perkins, as in Kleiner Perkins. Tom came into our workshop, and if anybody on this planet could look at the workshop and figure out who was BSing who, the real thing, I think it was Tom. Tom and I differ on this. I think it's fair, and I think he would support it. We've become friends. He would say it took him 35 minutes. I think it was 25 before he was so agitated. He's a very polite person, but he's quite insistent. Can you be in my office in San Francisco tomorrow? Yeah. 10 o'clock. Okay. Contracts. 25 minutes before he was asking for contracts. He wanted that machine that we were actually building for ourselves. You know, the Maltese Falcon is Tom's exquisite sailboat. He's a serious sailor. He's a serious pursuer of technology. The Maltese Falcon is known in the press as the biggest sailboat, but trust me, it's exquisite. You may remember she sailed under the Golden Gate Bridge a little while ago. Karen and I were on board. Tom was showing her off to his hometown. But she came in here to pick up the sub, and there is Tom in that sub. There's the Falcon. And here is that sub, the one that I thought was the most beautiful thing on the planet, the one I really wanted to build for myself. And here it is, and here's our team, and a couple of these guys are sitting in this audience right now. That's the team. That's the sub. It was Pier 37, I think. She's on Pier 37. Maltese Falcon is next door. We're going to pick her up under a crane that's on the forward boom and put her on the deck. We put her on the deck. We got to sail out. Spent a month on board. What a month. Take it down to the Sea of Cortez. Now, here's a man who's got everything in the world, but now he has the first really cool underwater aircraft. Really cool one. And he wants to know what it can do. But first of all, we've got to test it. We've got to get the bugs out of it. We've got to learn to fly it ourselves, and then we've got to train them. I'd allowed a month for that. Short? I know. Tom allowed us about 2 days and announced that we were done. Seriously? This was a serious time. But here it is, I think, in the Sea of Cortez. I'm looking at a silver head in the back there, so that's Tom, I think. That's probably me. He sat still for about 2 dives. I figured it'd take 20 to train him. He sat in that back seat twice, and he was done. Fortunately, the guy is really good, and this is really easy to fly. The next thing that happens, we went through testing and trials in a really compressed time. Tom got bored with the Sea of Cortez. He wanted big animals. And I was completely clueless about the capability of the boat we were on and the mindset of Tom Perkins and the captain. Tom said, where can we find big animals? And I stupidly said, oh, you know, 10 years ago with National Geographic, we found this incredibly wild, it was dangerous, by the way, place in the Pacific where at the time I'd refused to put Deep Flight 1 in. And I said, I think we dive with scuba gear. There's clouds of hammerheads circling around there. It's a really cool place. But, and I didn't get past the but. Tom said, where is it? Chris, where is it? Chris, as captain, started throwing out charts found one of the Pacific. I put my finger on it. Tom looked at it and said, Chris, how long? It's just this quick. Chris said, 3 days. Tom said, go. Before I knew it, the sails were out, we were heeled over, and this boat was just barreling out for this dangerous place in the Pacific. We got out there. The morning we're out there, I thought, it's going to be okay, Graham. I don't have to do this dive. I don't have to show them how to do it. They're never going to anchor. It's way too dangerous. Sure enough, I'm out there, and I'm woken up morning, and Chris says, we're anchored. You need to get ready. Tom wants to go. So I'm on deck looking at this sub, looking at this wild place. There's this huge swell coming through. It's a pinnacle in the ocean. Because it's a pinnacle, it's attracted local sea life. And outboard of that sea life are the predators, the tuna, predating on this gorgeous sea life that's cruising around there. And outboard of those are the really big predators. Really big ones. Very cool. But there's a wild current running. There's this surge that's just careening up and down this rock. I can only imagine what the cyclic current is underneath. There's a huge current sweeping by, and every manned sub I'd ever built, remember there's 60, if we put it in the water, it just would have gone, whoosh. So this was a lethal place to launch a sub. I'm standing by the sub, and I'm trying to figure out how to tell Tom no. It's not a guy you say no to. I think he snuck up behind me. I haven't got a good poker face, so he read me like a book, and he just stared in my eyes and said, Graham, you built this sub to do that, didn't you? Yes. Okay, we go. So we did. Best dive of my life. The sub obviously flew out there. It's so strong and powerful. We just circumnavigated that rock underwater. It's the coolest thing. We went around the back. We broke communications. It's dark side of the moon stuff. Announced on the comms that we're losing communications. Be back in 7 minutes when we came out from the dark side. We circled shallow, found these small fish, went deeper. Down this rock, lurking in, are the big Galapagos sharks that look like great whites. They're menacing, they're big. We moved outboard of the rock, outboard of the big predators. We'd learned to fly these machines, by the way, with big animals, and there's a few principles that you learn very quickly. One is that if you're going to approach a big animal, a shark, and you want to signal that I'm friendly, I'm okay, you get on the same level. You don't really get in front, you get back to show perhaps you're a little subservient, and you keep to one side, but you keep easily within their eyesight. You don't worry them by losing their eyesight. The opposite attack posture is down underneath, behind them. We found ourselves down underneath a school. It reminded me of a motorcycle gang of big hammerhead sharks, both wearing huge grins on our faces, saying, you know, we must be the first human beings in the history of this planet to stalk big sharks underwater. Anyway. There's that machine. We put lasers on. I haven't got time to go into those, but Charles and I were testing this out. He screamed, and I did. I said, Charles, put the lasers on. We both screamed. Straight out of Star Wars. Completely freaked me out. I've given you 2 customers. So who's the early adopters of these things? Well, there's a clue. There's another one there. Probably recognizable. The silver-haired knight on the left. And I got to run through this short. But he took one look at a Super Falcon on board a yacht and wanted one. But wouldn't fit, couldn't have the weight. And so we just came back. This is a few weeks ago, perhaps last week. It's a 3-seater open cockpit trainer. Darn cool for scuba gear. So where is all this going? Well, remember we started this with weight. We're one of the few people, I think, to start worrying about scale. You have Google Maps, and we could do with visually sampling this ocean and sticking it on, coming up with that data. But it's not going to work. It's not going to work if the cost just limits this to a handful of people. So we got 3 customers, but they're our early adopters. What we're aimed at is lower cost and scale. We're aimed at big numbers, trust me. One, we don't get to big numbers, but we do try and expand this. This is the second Super Falcon, is Karen and mine. I've been just in love with this machine. Here it is, early dawn, Monterey, and we're running a flight school. So if anybody here wants to come fly one of these things, just contact Karen and we'll arrange it. There's Taylor. Some of you may know her, local. That's John Scully with his son. We're just, this is that sub this summer. We're just having a ball. We've got scale. We can operate now from ships of opportunity. We've taken mancraft to this next generation. We've taken them through the barrier. And now I tell you quite frankly, we're going to take unmanned systems through the barrier. And these are the things that are going to unlock the ocean. This is what's going to give us scale. And I'm going to finish right there. So thank you for your attention. And I'll take any questions if anybody wants to tell me we're idiots or we're wrong, or you got any questions.
There's a number of universities that have built very long, there's a number of university groups that have built very long endurance underwater gliders that,
Yes.
Well, they refer to them as that. Do you have any opinion about that particular direction of research?
Yeah, it's great. It really is. That's one way of getting scale. There are 3 basic craft in the ocean, manned submersibles. We've broken through to the next generation of ultralight manned subs. But there are remotely operated vehicles, and there are what in our industry we call AUVs, autonomous underwater vehicles. Unfortunately, all 3 have pretty fundamental problems. The conventional manned sub is just too heavy, but we described how we've knocked that one down. The remotely operated vehicle, there is no physical principle whereby we can get enough bandwidth transmitted wirelessly through water to remotely pilot an unmanned craft, real time. So when we say remotely operated vehicles, unlike drones in the air, which can be piloted remotely, real time, you can't do that underwater. So the underwater remotes that exist are connected typically by an electromechanical cable. That mechanical cable works for the offshore oil industry, which developed those craft. It absolutely cripples them for going to high seas and for going deep. Give you one example. Japan built the deepest remotely operated vehicle, ROV. It's now been lost, but it did exist for a number of years. Its cable was wound on a winch that was 3 stories high. Remember, we started by saying the motherships kill everything. So if you have an ROV whose support equipment needs its own mothership, from our point of view, you've wasted your time anyway. So ROVs have a problem. AUVs, the gliders, are the answer to the ROV cable. These are craft that can be quite small, and they're let loose. They are limited simply by artificial intelligence. They're robots. So it looks like, it depends what you think about AI, but it looks like it's going to be a very long time before, robots will intervene in the ocean. So we're really focused on what the industry calls intervention. That is where, let's imagine there's a smoking chimney, and we want the DNA samples from here, and we want the mineral samples from there. That, at the moment, is out of the ability of an AUV. It requires a ROV or a manned vehicle. ROVs have huge problems. We think we can solve those. We've just been through massive problems with the manned subs. How difficult can it be?
Two questions. One is, are you concerned about maybe a squid or something wrapping itself around your vehicle and tearing it up? Or, and the second one is if you could talk about your power supply a little bit.
The squid thing is just a fabulous question, but you get me going on a giant squid. Look, our biggest problem with a giant squid is to make sure we've got cameras rolling when we get that close. I mean, I don't think it's going to wrap itself around. They are big, they are powerful, they're very smart in their environment. The idiotic thing is we think they're rare because there have been no human encounters to live to tell the tale. I have to add that last little bit. There's no human encounters that have lived to tell the tale with giant squid. The giant squid, the kraken, is real. We've got enough bits and pieces. We know it's real. Our theory is they're predated on by blue whales. They're probably not rare at all. It's just that we've gone in the ocean with dumb, stupid, slow machines radiating noise and light. These babies have eyeballs this big, same structure as your and I eyeball. They're clearly collecting the low light from biological light. And the last expedition used two of my subs, no, one of them, Deep Rover, to go and film the giant squid in New Zealand. And it's the funniest thing if you watch that. These guys really did know better, but it's just, humans can be incredibly stupid sometimes. So the sub goes down to film a giant squid, right, with a big eyeball. The eyeball's used to low-level light. The camera taken down is going to get exquisitely high-definition video. It's designed for sunlight, so it has to be married by two big 2-kilowatt arc lights that are going to take down 10 to the 6 more light that never existed in this environment, and they're going to film a giant squid? Oh, come on. So they're sitting on the bottom, lights blazing, no squid. And if I had better cartoon skills, I had this dynamite cartoon of the sub sitting on the bottom, Mike Degree inside, talking dejectedly to National Geographic people on here, no giant squids yet. And out beyond light range, where the light is now attenuated so it's not searing the eyeballs, there's wall-to-wall giant squids, and the mums are trying to push their babies to be the first on National Geographic TV, and the babies are going, the lights, I can't stand the lights. So you'll find that we're really interested in very low light level, how we see as pilots in that environment. It's no good us taking down lights that illuminate that place as if it's sunlight. All that's going to happen if we do that, we're going to fly through a sterile environment. Everything that's big and smart has just got the hell out the way. Boy, we hope to see a giant squid is one of my things.
The frequency of light to which the giant squid or any other thing you might be interested in can see? In other words, we have an optical range between 650 and 400 nanometers. If you illuminate me with 1,000 nanometer light, I don't know you're doing that.
No, look.
And I can build a camera that'll look at 1,000 nanometers, right?
Let's talk. Look, we are talking about an environment and science which is so backwards, it's nuts. It's just nuts. It really is. So look at manned subs. Do you realize all the manned subs that have gone down with their ears plugged? These pressure holes do not transmit sound. Charles here is trying to get us hydrophones, transducers on the outside. We want to listen to the environment. So that hasn't even been done yet, let alone what wavelengths and what cameras can we build. It's just a wide open field. Trust me, it's just, it needs bright people to come and help us work on it.
There, probably all the ones that aren't nuclear as well, got really fabulous headphones on, right?
Yeah, we have a budget problem, but
So clearly they're already gathering this data that you want.
yeah, they are. What we want to do is we want a simple binaural hydrophone array displayed so that we hear, the pilot and crew hear that naturally. If we're down and there is a humpback whale singing, we want to be able to know where it is. So that's our goal. It's a great goal. It also means we won't surface underneath a jet ski tearing at us as well. We'll hear that thing coming. But I just illustrate how crude, how backward this stuff is. Karen and I went to look for a shipwreck, by the way, and I know some of you are mapping in the South China Sea. It's a lovely story. We've got squabbles with pirates, all kinds of things. But the thing that's interesting is that the charts, the bathymetric data that anybody, Google or anybody, trying to do a bathymetric map of that area, will look at the area we're operating in, Royal Captain Shoals, and put the bottom at 600 feet. At 600 feet, we just happen to be down there exploring, looking for a shipwreck. At 600 feet on this seamount, the slope was still 70 degrees. 700 feet, 800 feet, 900 feet, 1,000 feet. Remember, the bottom's supposed to be at 600 feet. 1,100 feet, 1,200 feet, 1,300 feet, 1,400 feet, we found a shipwreck, and the bottom's still going down. Just illustrating, we live on an unexplored planet. And lots of that stuff, the infill on the ocean bottom, is just artistic fill.
So I have a couple questions. If light spooks animals, then how do you see, what is the point of having a human look out the window if there's nothing to see?
Well, look, the giant squid has got an 18-inch eyeball. They are using light. And if we dark adapt, I've been on a dive where we just turned all the lights out and just let our eyes dark adapt. I think there's kind of an overlap. So we just have to put lights on the sub that operate in that much lower range and let go of the idea of filming exquisitely beautiful James Cameron style. There are cameras that can see obviously much lower than human eyes and get underneath the squid. But if there's a commercial function, then you probably should use a remote. And you won't find us or ourselves arguing that manned are better than cameras. That was an argument that was used 10 years ago, but cameras are evolving faster than human eyes, and they've already crossed over. It probably is your question. So, you know, unmanned solutions in the future will probably dominate 20-1. And the manned stuff will be left for those of us that want to go down, probably.
So my other question is, how hard, what is the comparable difficulty of attacking the problem of building a cheap support ship? Just figure out some way so you can lift 60,000 pounds into a small ship.
Well, that might be another solution. Or another solution is you just get bigger so that the sub doesn't need a support ship and it's just autonomous. Another way that we're getting rid of any costs at all, we're trying to get the cost really down to where it's just affordable. So another way we can do that is improve the range of the Super Falcon so that we can operate close to a canyon, as in Monterey, and we'll just go from shore. We'll just fly out there. But there are solutions. Big autonomous submarines, that's beyond our budget, and unmanned systems, which are very small and economical.
Hi, question from New York. Can you hear me?
From New York?
Yeah, that's right. I was wondering what happened to Steve Fawcett's submersible. Was it ever used?
No, it's sitting in a workshop. It's owned by the Steve Fawcett estate. We own the technology. The machine is sitting there gathering dust. We don't know its outcome yet. Stay tuned.
What's the education, skills, training, experience for your members of your team?
Our engineering team, we just try and get the brightest we can in young before they're messed up and cut them loose. That's about what we do.
More questions?
Two questions. First, what is this dangerous place that you visited in the Pacific?
Oh, the Roca Partida. It's about 200 miles southeast of Cabo San Lucas.
Okay,
it's
great.
It's part of the Socorros Islands.
Okay, thank you. And the second is, tell me a little bit more about propulsion, communications, human endurance factors of your latest submersibles? How long can people stay down?
Well,
and do you compress those at all? Because
do we what?
Do you put any compression on those at all? Would you?
Oh, no, no, no. No, if you fly a commercial aircraft, your cabin pressure is going to fluctuate between 14.7 and maybe 10 or 12 psi. Fly a Super Falcon is kept within 0.5%. Because it doesn't need to be, but we can, so we do. It's a little microcomputer, very clever, so it keeps it very tight. And we're only, by the way, the life support in there is the same as a closed system, same as a spacecraft, so there's no bubbles. We're only consuming oxygen. We're metabolizing oxygen cylinder this big. It'll last you 24 hours. And propulsion has been a big, energy storage has been a big problem. Batteries, electrical systems are preferred. They're simpler. We know how to build those. So, the modern lithium battery has been our savior. It's why we can fly. The prototype D-Flight 1 was to fly with Alcoa's aluminum oxygen seawater batteries. They never materialized, but fortunately, they required a buffer battery pack of lead acid batteries. So D-Flight 1 flew with lead acid batteries, 20-minute endurance. We have the same problem as Wright brothers. Our subs are more energy, use higher levels of energy than a conventional submersible. But with the lithium chemistry we're getting on Super Falcon, Tom made 2-3 dives a day. We just came back with the sub we delivered to Branson, and we actually ran training on that for 2 days, and we never charged the batteries. So we're home and dry on propulsion, thank goodness. We waited for 20 years, though. Yeah. So when am I going to be able to buy a Super Falcon for the price of a luxury car? We're going to buy a Super Falcon for the price of a luxury car when they're made in batch quantities of 200 or 300. Just that simple. I don't know when that's going to be. But you know what? We're going to have a lot of fun with the one that exists before we get to that point. And
I guess related to that question, other than the pressure hull itself, is the rest of the equipment that goes into it off the shelf, as it were, as in used in marine environments now? Is there anything else that you build yourselves?
No. No, and that's the barrier to entry in this. There's nothing. So it's not like aviation or where we can buy avionics or an engine from somewhere. For example, the advent of flight, we needed an artificial horizon. Not available. We couldn't use vacuum-powered ones for aviation. Had to build our own. So Charles is writing the code for. No, we can buy nuts and bolts. We can buy semiconductors. That's it.
More questions? All right. Let's thank Graham again.